observations we've done mainly on the Nordic Optical Telescope for over several years, and it's sort of very timely now that because I just noticed when I was observing with the knot last week that on this week really, it's exactly 20 years now since I first observed with the knot. So it's sort of it's not. I'm not going to sum up all the 20 years of observations. Don't be worried. But I think it sort of nicely coincides with the topic of the talk in that sense. Okay, we have I have a list of collaborators. Sauni Somero, who's my student back in University of Turku. Then Phil Charles from South Africa Observatory. And Diana Hannikainen from Finland, who's at the Metsähavi Radio Observatory. And Panu Muhli, who's sort of out of astronomy these days, but still keeps in touch. And National Survey of Finland. And Linna Jalmasdotter, who used to be our student in University of Helsinki in Finland, and is currently not involved with any institute, but still keeping up with things. Okay, the title is Optical and Near-Infrared Studies of Short-Period Low-Mass X-ray Binaries. And if I have a quick look over, I'm sure most of you, probably, or some of you anyway, know what these systems are, but I'll just quickly recap. Low-Mass X-ray binaries are something where you have typically a main sequence, secondary star or slightly evolved secondary star filling its Ross lobe, and then you have a primary star here, which is either a black hole or neutron star, and then you have an accretion disk here around it, and sometimes some corona, and sometimes some jets as well. So they're basically the same similar sort of systems that, if you've heard of cataclysmic variables, they look roughly the same, but as a primary here, you would have a white dwarf. And in the name LMXB, the low mass X-ray binary, the low mass doesn't really refer to the primary, but it refers to the secondary. And so you have this sort of rather late type main sequence low mass stars. Okay. And I'm going to talk about a couple of different systems, 4 or 5 to be exact, that we have data from NOTS and some data from VLC as well. And I'll quickly go through this. We have basically an X1916-05, which is about 50-minute period low mass X-ray binary, so it has a degenerate secondary star, and it's a dipper and some sort of possibly also an ADC accretion disk corona source. We have a UW Corona Borealis, which is just under 2-hour period system, and X1822-371, which is 5.6 hours. Accretion disk corona source, and also has an X-ray pulsar in it. And all these 3 systems have a neutron star primary. And then we have 4U1957+115, which is 9.3-hour period system and a possible, likely black hole candidate. There are no radial velocities or detection of the secondary of this, but based on the X-ray spectrum, which is very soft, there's been suggestions it's most likely has a black hole primary. And finally, we got 0614+091, which is a bit of a strange source. We don't know the period of that. It has CNO lines in the optical spectrum, so it's probably also a double degenerate system with an orbital period of less than an hour. But I'll return to these in turn, and we can discuss them a little bit later. So the topics, I'm mainly going to concentrate on the optical light curves of low mass X-ray binaries. Look for the evidence of drastic changes in the accretion disk structure, in particular photometry of UW Corona Borealis, and also some photometry and infrared studies of 1957. Then I'm going to talk about some high phase resolutions, VLT spectra and Doppler mapping of 1822-371. I'm going to wrap up with some fast photometry of 0614+091. And so we start with the optical light curves of low mass X-ray binaries in general. Back in the 80s or early days, the traditional view was that most of these systems, the optical light curve, just comes from the X-ray heated phase of the secondary star. Because you have X-rays here illuminating the secondary, and so the idea was that in most of the systems you just see a sinusoidal modulation because of this heating there. And of course there's emission from the accretion disk. Most of the optical emission comes from the accretion disk, but it was thought that the accretion disk is rather uniform and doesn't really contribute too much to the changes, and we would see it's a sinusoidal unless the inclination is high. But this picture has really been changing all the time, and I'm trying to show you or convince you today that it's really not the case at all these days, that all these light curves are much more complex than just what was produced by the X-ray heating of the secondary star. So there have always been some exceptions to this rule. I said that the idea in early 80s or so was that most of them would be sinusoidal. There actually was surprisingly little optical photometry of these systems, because I remember I read when I was a student, I read somewhere there's no point observing this because it's all sinusoidal anyway, and but times do change. But this exception was there already in the 80s. This is very old results from, or very old modeling of 1822-371 from the 80s by Cole Hellier and Keith Mason. And you can see up there's an X-ray light curve of the system. So there's a strong modulation combined with some partial eclipse. And here's an optical light curve with some model fits. These people used to fit this with some sort of a flared disk model where you have disk opening like this and has non-axisymmetric thick outer rim of the disk to model the X-rays coming from the corona here and the optical coming from the accretion disk, both outer and inner part of it, and also partly from the secondary. But this was also always sort of an odd one out. And theorists never believe these models because they require quite thick disks, and it's not very physical to have disks like that. But then there are other exceptions. There's always been Hercules X1, which is a 1.7-day period. Lomas X-ray binary has a 35-day cycle in X-rays, and it's been known already from the 70s. And it was thought that this 35-day cycle was due to a tilt accretion disk that's precession like this, and so the fraction of the X-rays you're seeing is changing. And also the optical light curves you see here, there's an old paper by St. John from 1976, some 3 different phases of the 35-day cycle. You see changes in the light curve shape, and this been stolen from the X-ray binaries book by Lewin et al., an article by Jan Paradise and Josh McClintock. And shows also B-band light curve of Hercules X1 changing quite a lot over the 35-day cycle. So these 2 exceptions have been well known before, and well, here's the third one for you then. This is the 1957 plus 11.5, the black hole candidate source. There's not much photometry here for a long time. There's only one early set by John Thorstensen, which showed the sinusoidal modulation I referred to earlier on, and with some amplitude. And we then decided at some point during the late 90s that it's time to have another look at that system, and it was basically looked totally different. The light curve is no longer sinusoidal, and the amplitude is more than double the previous amplitude. So I'll return to this soon, but I'm just going through these examples first. Here's another sort of 1916-05. This is actually X-ray data from RXTC satellite, and you can see here that also the X-ray light curves of these systems change quite drastically. Here's one folded light curve, and below is the next night or next day. So there's lots of changes there. And we have some optical data during those observations as well from the Nordic Optical Telescope. And also in here you can see that from night to night, the X-ray light, the optical light curve changes quite a bit in shape. So I'll start with well, that was just to illustrate that there's lots of variability actually going on in the light curve shapes, and I'll start going through some individual systems now. And I'll start with UW Corona Borealis, which was found in the exercise medium sensitivity, Einstein medium sensitivity survey in the 80s, and that's the old name. Some of you might recognize as MS1603. It's 111-minute system, V19.5, has a very low NX to L optical ratio. I mean low for a Lomas X-ray binary. It's an accretion disk corona source. It's a high galactic latitude. It's in the halo basically, and it turns out now it has a 5-day superorbital period. We got a couple of years back, we got some X-ray data. This is XMM Newton data of UW Corona Borealis. And we had 2 epochs, 2 observations separated by 2.5 days, because we had some indication from the optical light curves earlier on that there might be a 5-day cycle in the system. So we have here is soft X-rays 0.2 to 1, 1 to 3 keV, 3 to 10, and this is the OM XMM optical monitor white light combined optical and UV light curve. So this is epoch 1 on the left and epoch 2, 2.5 days later on the right. So you can see in the soft X-rays there's a huge change. There's also some change in the higher X-rays and quite a big change also in the OM, UV and optical light curve shapes. And I'll skip the X-ray spectrum here. It's just to say that we need several components to basically, you need a black body and you need a power law and you need a mechanical thermal component or plasma component to explain the X-ray spectrum, but I'm not going to talk more about that. But this I want to show you, this is the knot light curves we collected over the years of this source, UW Corona Borealis. This all folded on the orbital period, 111 minutes. There are 2 sets. The set on the left is 6 consecutive nights. This already done in 1999. This is the first night, second night, third, fourth, and so on. And we had a similar but longer run in 2002, which is basically this all done in white light, and you see there's quite drastic changes in the light curve shape, going from really strange-looking eclipse profiles into almost no eclipse at all in the light curves. And the interesting thing here is that if you come on the right here, if you look at the first night here and the 6th night here, they start to look somewhat similar. And this is also the same shape that the 1957 light curve we've seen in this black hole candidate 1957 plus 11.5. And of course you can't really do a proper period analysis based on this, that we have 8 nights of data and we want to look for a period. We've done various statistical tests. I know it sounds bad, but various different methods to look at if there would be any repetition or correlations between the shapes of the light curves. And you always come up with a different, always suggestion that light curves that are 5 days apart have some similarity between them. And it's also been confirmed. There's another paper by Paul Mason last year that where they have data from the US, different sets of data, and they come up with a 5-day cycle for the shape of the light curve as well. And I think this is a prime example of how variable the light curves can be, because there's no change in the overall flux level. The system brightness remains the same. So there's no change in accretion rates or anything. It just has to be the disk that's doing something that's causing all these different variation in light curve shape. And of course, this is a high mass ratio system because it has a neutron star and a 111-minute period. So the mass ratio is very high or small, whichever you want to put. But anyway, the 2 stars have vastly different masses, and so it's likely that it's the disk precesses and so on. But it's not simple disk precession can't really produce all these details here. So I think there must be some sort of either warped disk or somehow otherwise very non-axisymmetric disk that's somehow wobbling around in the system to produce all these light curves. There are no really proper models yet, but we're working on trying to model these in detail, but that's sort of not the topic of this talk yet. Another interesting thing about this system is that there are it's quite frequent bursting. There are lots of X-ray bursts here that you can also see in the optical, and we have altogether detected 21 bursts, which is still not too much, but again, you can do some simulations with 21 bursts and try to place them randomly over the orbital phase. And there's already some hint here that most of the bursts seem to occur the first half of the orbital period. I know it's only 21, but there's a couple of % chance that it's still uniform distribution. But we're looking forward to more bursts and then see if it really would be the case, because this sort of makes sense, because typically in cataclysmic variables, probably also in enormous X-ray binaries, there's this one phase where the mass stream from the secondary is hitting the accretion disk, and there's supposed to be this bulge on the disk on that side. And that side, if that's higher, thicker than the other side of the disk, it would, in a high inclination system, could introduce something like this that you can't see really often. I mean, it's more likely that you see the first half of the orbit when the bulge in the disk is not in the line of sight. But again, here we need much more data. But if I conclude quickly with this source, basically what we've seen is very highly variable optical, also X-ray light curve shapes. A possible 5-day superorbital period, this is likely due to disk precession, and much more data would be nice. This is 90.5, so there's not really spectroscopy yet. Needs a big telescope to do that, so you with the grant account might be interesting. But anyway, we'll see when the spectroscopy comes, what comes out of this. But I'll move on to the next target. 1822-371 is 5.6 hour orbital period system, accretion disk corona source. This is the source I showed earlier, all this data by Hellier and Mason and these models with the disk rim. We had a project to look at this with the VLT because there's published Doppler maps of this system, and but if you take the standard Doppler mapping approach to the mapping the disk, you assume that you see all parts of the disk at every single orbital phase. But if you have something like very thick disk rim, you have some obscurations, phase-dependent obscuration of some of the disk, and your resulting disk maps from fitting the spectral Doppler mapping could be affected by that. There's also partial eclipse, so we want to have high time resolution spectra through the eclipse so that we can see if there's any effect on the lines. And so we got some VLT Forest 2 data with 2-minute time resolution, which is quite nice. Here's an average spectrum down here. And this is what, by the way, this is not my work, but it's my work. This is what's only been doing. And so I'm just explaining a little bit about that. So there's a light curve there from the continuum near the, well, there's the range, basically. And so this optical light curve, again, has changed shape because if I go back here, this plot here from Hellier and Mason contains data that's 5 years apart from each other, and you can still plot it on the same curve, and you can't tell which points are from 82 and which are from 87. So it was thought that this is very stable shape, this light curve. But if you now compare with the going wrong way, compare with this light curve, it's quite different in shape now. And also, Auni's been working on some archival XMM data, and if you take the XMM optical monitor light curve, it looks like that as well. So there's, even in this system that seemed to be quite stable earlier on, there are changes in the light curve shape. And here are some trailed spectra. These are basically normalized to the continuum, so that it's basically, continuum is 1. And this is actually, effectively, this is equivalent width that's plotted here. And the interesting thing here is that the eclipse is there. This is the eclipse phase. So what you see here, this is a helium-2, Bowen blend, and H-beta here. There's lots of absorption in H-beta as well. Particularly if you look at helium-2, what happens is that basically, I think, oh, there's H-beta there. I might have a wrong plot here, but anyway. The line flux remains constant over the orbital period. Even if the optical light curve is doing this, the helium-2 and H-beta lines, especially helium-2, are not eclipsed at all. Nothing happens to the line flux during the eclipse. But still, and here's the Bowen blend for comparison. You can see the Bowen blend line, there's the same modulation as in the light curve. And here are 2 Doppler maps. So on the left you have the Bowen blend map, and it seems it originates on the X-ray Halley phase of the secondary. Probably some of it's coming from the accretion stream before it hits the disk. On the right, there's helium-2, but that's the surprise. This looks exactly that it comes from the accretion disk. This is a typical Doppler map on an accretion disk. But we know from the light curves that the accretion disk gets eclipsed. But on the other hand, we also know that the lines don't get eclipsed at all. So what's happening here? And I think the explanation might be that we are looking at something that's a bit like a helical wind from the disk. Wind that goes up but still retains some of the rotation of the accretion disk. Because the other thing is that if you look at the velocity scale here, the bulk of the velocity is about plus minus 300, 350 kilometers per second in the Doppler map on the right, which is far too little for the disk around a neutron star of, say, 1.5 solar mass. So even if it looks like a disk, it has the same velocity structure, but the amplitude is a bit too low. This velocity would put it almost inside the secondary star. And so it has to be, so we think that this together combined with the fact that the line is not eclipsed at all is probably because the site for the helium-2 emission is somewhere above the disk, and must be some sort of, maybe a disk wind with some velocity still from the helical disk wind. But I can't remember seeing this in any other source, but yeah, I think it's kind of interesting. So I'll just conclude with 1822, what I said already, that I think the main result here is that that the helium-2 lines aren't really coming from the disk photosphere, but they have to come somewhere further up, but still with some sort of velocity that originates from the disk. Okay, I'll move on to the next target. This is for you 1957 plus 11.5, the 9.3-hour period system with V18.7. And there's been quite recent paper by Mike Novak where they modeled the X-ray observations of this system and X-ray spectrum, and they come up with the spectral fits that they can basically fit the X-ray spectrum either with a 3 solar mass black hole at a distance of 10 kiloparsecs or a 10 solar mass black hole at a distance of 20 kiloparsecs. But anyway, the spectral, I'm not that familiar myself with the X-ray spectra of this type of systems, but that seems to be the conclusion there anyway. There's no radial velocity information on this, even if it's at 18.7, but this is a persistent source, so there's a bright accretion disk all the time, but I'll return to the property of not seeing secondary soon. First to the optical light curves, though. This is the plots, well, some of it you saw earlier on. Here's the old optical light curves by Thorstensen from mid-80s, and sometime during the late 90s we did UV-VRI observations at the knot, and this was quite a surprise because we thought it's very nice we can have 5 colors, but as you can see there's really no difference at all between the U and I light curve, for instance. It's very much the same modulation in all the colors, and the amplitudes are plotted here. The modulation amplitudes UV-VRI are roughly at this level, and this is what Thorstensen saw earlier on in V-band. So it is more than double the amplitude, and the shape is totally different, and there's no color dependence whatsoever in UV-VRI. We've done some ring modeling years back, again with similar sort of modeling as the Hellier and Mason for 1822, where you try to fit the light curve shape and come up with some sort of a shape for the disk. And this basically doing it several times, sort of bootstrapping, and we come up with a number of disks. This is basically the height of the disk as a function of azimuth there. It's not very fancy modeling at all. I'm not going to talk too much about that old stuff. Come up with some system parameter distributions from those modelings, and at that time we thought that, well, we come up with an inclination of 70 to 75 degrees, which is probably right, and with some other parameters, Q and disk radius and so on. But I'll leave the details out here. But what's more interesting in here is that you saw just that there's no difference in the light curve shape going from UV-VR to I. But let's go to J then. And here's the J light curve. And that's also, the J, the data is the black dots with errors. And the red diamonds are R-band light curve taken during the same night. Because in the knots you have knot cam in the cascade focus, and you have the stand cam all the time. So when we made the observations, we took R image every now and then with the stand cam. As you fold on top of it, you see that there's absolutely no difference even going to the J band compared to the optical light curve shape. And if you then make the spectral energy distribution from that data, you see that there's absolutely no sign of secondary star whatsoever. Going all the way from B to K, you can basically fit it with a power law that agrees with a accretion disk model. But this is the case in many other systems as well, but the interesting thing here is that we're talking about a 9.5-hour period system, which means that the mass of the secondary is roughly 0.95 solar masses. If it's main sequence, its absolute magnitude is roughly 5. If it's at 10 kiloparsecs, its apparent magnitude would be 20, the secondary alone. We know there's no absorption here at all. It's very blue source, and in the X-rays there's practically no extinction at all. So where's the secondary? Because if it's at 10 kiloparsec, it should be 20 magnitude in V, and the system is 18.7, which means that roughly about 25–30% of the flux in V should come from the secondary. Not to mention what you see in the infrared. But there's absolutely nothing here. So what I think what this tells us, combined with the spectral fits by Novak et al. On the X-ray data, where they say that at 3 solar mass black hole primary would put it at 10 kiloparsecs, and 10 solar mass black hole would put it 20 kiloparsecs. I think I can quite safely say here that unless the secondary is something totally weird, it's more like 20 kiloparsecs than 10 kiloparsecs, because there's absolutely nothing from the secondary here. There's another interesting thing here. We also had some fast photometry of this system. This is time resolution of 5–10 seconds. And we did some period analysis of that. And there appears to be one peak here, which is corresponds to 11.5 millihertz, that's 87 seconds. And the lines here, these horizontal lines here, we did some red noise modeling of the light curves. We're fitting some sort of so-called AR2 models, autoregressive models for the time series to model the red noise, and then use that model to create synthetic light curves with the same statistics and same red noise as in our real data, and we use those to estimate confidence levels for these peaks. So this is 2, 3, and 4 sigma levels for the confidence. So this is roughly, I would say, roughly 5 sigma detection, with and this is the fold, the data folded on twice that period. So there might be another millihertz QPO there. I guess I'm not quite sure. I think Tarik would be the right person. Maybe it's a microflaring in the disk or something like that. But this is the only fast photometry data set of this system I've come across, and we only have this one set as well. So it might be worth another go with ultracam or something like that to see what's in there. Okay, if I conclude this source, so another one with clearly changing light curve shapes, and there might be some sort of superorbital period here as well at what's it happening, at what the changes in light curve shape are happening. We don't know yet, we don't have enough data, and I think the non-detection of the secondaries really supports the idea of a quite massive black hole in this system. Finally, I quickly show some data for the really odd source, the 0614+091, which is another 18.5 magnitude low-mass X-ray binary. It has a long period, about 10 days, detected from JKT observations by Mason et al. And much more recently, the optical spectrum, which doesn't show any hydrogen lines, seems to show CNO lines, which means that it's probably an ultra-compact system with a period less than about 60 minutes and a double degenerate secondary star, a bit like 1916-05. That's anti-correlated X-ray and optical flux, and various peaks in power spectra. There's a recent paper by Tarik last year, which I think is the only published paper on photometry on any periods. Because there's I put the last point. There are lots of rumors of periods around 50 or 51 minutes here, but I know of several data sets that have never been published but have been maybe presented on some conference, or I heard somewhere that there might be a period like this. Okay, this is the X-ray optical anti-correlation. This is the old Ecosat data and from 1986, and this is simultaneous V-band photometry from JKT. So you can see when the X-rays are going up, the optical is clearly going down. Okay, I'll go back here. The interesting thing about Ecosat data, though, is that if you take just the part where the source is brightest in X-rays, that's this part this is actually 3 observations of X-ray, one ending here, another one ending here, and the third one ending here. If you take the last part and zoom it in, you actually see something like this, which at least to a person who's done lots of photometry, you can immediately see that it's not just noise, there must be something there. And if you do a power spectrum, you come up with a period of 24.5 minutes. And again, that's the red noise limit, we've done the red noise modeling of there. So it's just above the maybe 4.5 sigma detection there. So that's 24.5 minutes in X-rays. Okay, so some of TARIC's data. And there's several data sets here, and from different observing runs, there seem to be different periods appearing. The strongest one being the 51.3 minutes. There's also sometimes 42, and sometimes 64-minute period. And then there was the 24.5 in the exercise. Okay, if I then go to what we have now, I'm about to write up this thing. We have 10 data sets of white light fast photometry from NOTS, covering several years. It's been our sort of standard backup target we've been observing over the years. There's all sorts of behavior there. I think most interesting is the down here, where you can see beginning of the run, there's some period that seems to fade away and come back again towards the end of the observation. I have power spectra of all of these, again with the dashed lines, the 2, 3, and 4 sigma limits from the red noise modeling. And there's, okay, these all quite short data sets, they're only maybe 2, 3, 4 hours at most. And so the peaks are very broad, what do you see there? But, okay, here's 60-something minutes. Here's quite strong, I think it was 37 minutes. Here's the 51 minutes that's been reported by Tariq and others. There's again something at just over 40 minutes, 42 minutes was one of Tariq's periods. There's another, I think it's 45 minutes or so. And finally, this is the interesting one in the one down here where the periods seem to fade away and come back. And that's actually, that period that is there is 14.5 minutes. So you see, there's a number of different periods that's at least based on the significance level estimates seem to be significant, and I think this source really needs more observations, because there seems to be lots going on here. It's probably a quite small inclination system, so that we see it almost face on, and that's why we can't clearly see the orbital period. But I don't know, I probably would put my money on the 50 minutes as well, being the orbital period, but there clearly are other periods as well, and I don't really have an explanation for all these different periods, why they appear and go away, and really need a very long observation to sort that out. So, just to quickly recap on this, so there's a 51-minute period evidence in several data sets, and that together with the fact that there are no hydrogen lines, only CNO lines in the spectrum, seems to suggest that it probably is an orbital period. And here's once more the zoomed in our last data set, where you can see the period fading away and probably coming back towards the end. We've done some wavelet analysis of this as well, which seems to show that, I don't have a plot of it, but seems to show that there's a significant period in the beginning and in the end, but not in the center. But I think it's a quite interesting source. Okay, I think I'll summarize everything in the end. This is roughly all I wanted to say. But I think the main point here I want to come up with these different 4 or 5 systems is that, unlike I was told, or I read when I was a student, that all these systems are boring with the sinusoidal optical light curves, I think it's not really true. And I think it's just that if we observe these long enough or frequently enough, we find that I would almost put my money on that every single low mass X-ray binary with a period less than 12 hours, I'm sure it will have a evolving light curve shape in the optical, and the disks aren't really as what they used to seem, at least in the 70s and the 80s. But there must be some warping and precession or whatever. They're much more alive than we probably thought early on. I think that's roughly all I would say. Okay. I need to see if I can. I don't have it written down, but we can have a look. No, we can't read. Yeah. We haven't gone that far yet. We haven't checked it. So, yeah, hard to say with that scale, but need to check with Army because I haven't really been physically involved with the with the data myself. But we can ask Army and I'll let you know about that. I think it's quite interesting result this anyway. So. But do you agree? I mean, do you agree with the?
Yes, with the interpretation that, yeah. Mm-hmm.
Sorry? Yeah. I can't remember that. No, sorry. But this amplitude here is roughly about plus minus 350 kilometers per second, which is. And I think you have a paper, or your students has a paper on that you were claiming that it's actually the much more massive neutron star. Is that true?
Yes.
Than the standard 1.4
yes,
or 1.5.
Yeah. Yes. We set a limit on. I think it was like 1.7 or 1.65 plus or minus 0.15.
Okay.
So it could be down to from 1.5 to 1.8.
Yeah.
And that was based. Well, this is a very interesting system because the inclination is known pretty well, and also the neutron star is a pulsar.
Yeah.
So we know the orbit of the neutron star. So the only missing information was the rate velocity curve of the companion star.
Yeah.
So we used the bound blend to trace that.
Yeah.
And combining all the information using a K correction because this line is produced in the on the radiated phase of the companion, not from the center of mass of the companion. So you have to apply a K correction.
Yeah.
And combining all this information, we end up with these limits for the mass of the neutron star, which turn up to be massive.
Yeah. But that's because that makes this thing even worse then, if it's more massive, because the velocity is so small that it has to be even further out if it's in the disk, but you can't really fit it in the primary source lobe with that sort of velocities. That's the thing.
We actually noticed the same effect, that the velocities of the helium-2 line are smaller than you would expect in a disk.
Yeah.
So we thought about the same possibility. It might come from from somewhere above the disk.
Yeah.
And not sharing the Keplerian velocity of the disk, but somewhat lower.
Yeah. Okay. And it's quite clear here. There's really no. When you look at the lines during the eclipse, there's nothing gets eclipsed at all. It's sort of integrated over the continuum. The area of the line remains the same. Nothing.
Any more questions?
I have a curiosity. You showed us the spectral energy distribution in the optical and near infrared for these objects. Do you know there is a hit for also in the ultraviolet, optical and near infrared? The same graphics and also in the ultraviolet bands.
Yeah, sorry. Yeah, you okay. Oh, wrong way. Okay, yeah, we don't have. This is. When we did this observation, for some reason we didn't take any U filter then at all, and I don't know why. And we don't have any. No, we don't. I don't think there is any UV data probably, or combining. I mean, this is all taken during the same night, so it would be a bit dangerous to combine with any other ultraviolet data because the light curve is doing this, and the system state might change a little bit. So. There's no simultaneous ultraviolet data, so it would really. I haven't checked the XMN. There might be some XMN OM data, but then again, it's not taken at the same time, so we can't really say anything. But so this is basically just the line fits to the to the log scale. But I've done some sort of fitting where I have put a disk there with some sort of radial temperature distribution and varying that radial temperature distribution and the inner and outer radius of the disk. I managed just with the disk and easily fit the whole curve there. So, but yeah, but ultraviolet, I'm afraid no.
You showed several anomalous effects. Have you considered a model of a clumpy accretion disk? I know Cristina Ramos has been working on clumpy accretion disks for 8 years, and I don't know if they might explain some of the features that you showed us.
Yeah, I don't know. This changes because they said they are. Okay, which one I should choose? Bring up the light curves. These are still strictly periodic. I mean, it's hard to. I don't know if you can produce this sort of effects with the clumps in the accretion. I'm not sure, but it's actually very hard to try to find anything that reproduces this, because even with the warped disks, I think that if I'm not totally wrong here, the idea is that you have these warped disks that look like crisps or potato crisps. And they are precessing with say, superorbital period. But I guess the idea is that when you, as an observer, look at the disk, it's sort of the warp disk looks something like this, and the secondary goes around, and this warp then turns with the superorbital period. Warp is probably, it's not turning with fixed in the system. But if it's like that, it's very hard to produce this sort of light curves, because if the warp remains the same, why is there so much difference over the orbital period? Because if there's a secondary going around, of course the mass flow from the secondary hits the sort of different paths there, so maybe that's the reason. But it is, I find it quite hard to explain especially if you look at the old, the X-ray light curve of 1822, it has a very large modulation like this on top of the partial eclipse. How can you know the X-rays must come from the corona, or some of them from near the center, but to have this sort of modulation over the orbital period really needs a big structure to obstruct some of the X-rays. So in a sense, this old modeling is with this flared disk is sort of feasible when it comes to observations, but if there's a warp that's not rotating with the system, but remains sort of constant over one orbital period, I find it quite hard. How can you produce X-ray modulation like that? So basically my answer is that you need a quite large, big structure somehow that's moving with the orbital period to be able to produce something like this. That's my view anyway.
Thank you.
That's the other thing, yeah, that's true. Yeah, that's true.
Finally, separation with the Q.
Yeah.